Welcome everybody. Here we shall present our work entitled Stratified Multitask Learning for Robust Spotting of Syntax, done jointly by Kinjal Dasgupta, Sudip Das and myself Ujjwal Bhattacharya, all from CBPR Unit, Indian Statistical Institute, Kolkata. Here is an example of a natural scene captured by a handheld device, and it contains plenty of text. Spotting of this text, which includes localization, segmentation, followed by recognition, has enormous application potentials for its use by foreigners with language barriers, persons with visual impairments, etc. So what are the goals of this study? The goal of this study includes, number one, gaining control over the dynamics of multitask learning to unlock the potential of deep networks to a greater extent towards development of an efficient end-to-end learning framework for syntax spotting. Number two, dividing a block of network connections into a few strata so that the connection weights of its different strata may be adjusted corresponding to distinct individual subtasks, similar to the functioning of human brain. Existing FTL approaches of deep networks apply adjustments of all parameters of their feature encoding part corresponding to each of the underlying subtasks. Number three, efficient controlling of the training of different strata by introducing a novel regularizer in the loss function. Such syntax, in fact, vary widely with respect to their shape, size or scale, orientation, illumination effect, blur, background, occlusions, perspective distortion, etc. And the same can be verified from some of the examples shown here at the bottom of this slide. So what are the challenges? Challenges include extremely wide variations in style, shape, scale, and length of text. Its difficulties to train a multitask network, MTL, with respect to each individual task in a balanced way. Maintenance of a proper balance is important so that the network parameters converge to certain robust shared features that are useful across all the underlying tasks. Segmentation map of the text instances for all of the available benchmark datasets are not available, excluding COCO text. So here our contributions include, number one, development of a novel end-to-end trainable network towards robust detection, segmentation, and recognition of syntax. Number two, inclusion of a feature representation block called FRB in the proposed deep architecture. Number three, introduction of a novel concept of parameter adjustments of FRB in a stratified manner by borrowing the idea from the functional organization of human brain. Number four, introduction of a novel regularizer in the loss function of multitask learning to control parameter adjustments of different strata of FRB. Number five, suitable training of the proposed network to handle various states subjected to various situations like widely varying scales and orientations, occlusions of varying percentages, severe degradation in the image quality, and so on. So here we show the proposed deep architecture. This deep architecture has an initial block which produces 4 orientation channels from the input image. This block, extended features block. Next, the encoder block. ResNet 18 based module, it is used in the feature extraction part of this network. Its output is passed to the next FRB module. feature representation block. This FRB module consists of a number of Gabor convolution layers arranged in multiple rows, followed by a multi-scale feature representation module or MFRM. It consists of a 4T IRNN for extraction of contextual features and a channel-wise attention map. This enhances important features while attenuates noisy, unwanted background information. The 4T IRNN of MFRM extracts contextual features. And the final output from FRB emanates through an aggregation block and consisting of conditional random phase. This final output from FRB is fed to the decoder block consisting of a series of deconvolution layers. The output from the last deconvolution layer is fed to the detection branch. The output consists of a score map, the Arbox geometry, and the orientation angle. Detected text is recognized by the recognition branch of the network, which is fed with the output from FRB after passing through the same derecog and ROI rotate. So the text recognition branch, its configuration is shown in the alongside table. The encoder part consists of a 34 layer residual network and 2 bidirectional LSTM layers. Each of its residual units perform 2 successive convolution operations of size 1x1 and 3x3 respectively. The decoder part consists of 2 two-layer additional LSTMs, each of which comprises of 256 hidden units and another 256 attention units. Now, some details of the training strategy of our framework includes domain adaptation. In fact, traditional machine learning assumes training and test data come from the same domain or distribution. However, this is not the situation, as it can be seen from the example shown at the top of this slide. In fact, we used adversarial loss to minimize this effect of shift between the two domains. Here we have given some visualization for domain adaptation. To the left, in the middle of this slide, the figure at the left when it is not adapted, and on the right side it is when adapted. This illustration of domain shift, where the distribution of the unlabeled target domain is misaligned with the labeled source domain, but both distributions share structural similarities. Aligning of the two domains helps the decision boundary of the supervised task fits better across both domains, as it can be seen from the right side diagram. Further details of training the framework. We perform training of our MTL network in 2 phases. In the first phase, we initialize the relevant network parameters separately for learning each of the individual subtasks: T detection, T recognition, T segmentation, and the domain classifications independently, and store the respective sets of parameter values of the feature representation block only. In the second phase, we consider the whole network for training of the underlying multiple tasks for syntax spotting. Here, parameter adjustment takes place with respect to the loss function L multi, shown at the bottom of this slide, where lambda is the hyperparameter of the regularizer R, which is also shown here. Some additional details of training of our framework. We consider pixel-wise blurring. Here we have applied certain percentage of pixel-wise blurring in the input image for training with samples affected by deformation of varying degrees. At the bottom of this slide, To the right, we have shown an original image embedded with some natural syntax. And to the right, we have shown a image after applying 30% Gaussian blur. Also, we consider curriculum learning. Curriculum learning is a way of training a machine learning model where more difficult aspects of a problem are gradually introduced in such a way that the model is always optimally challenged. In this work, we employed curriculum learning with respect to progressively developed pixel-wise blurring, masking percentage, and complexity of images to allow the feature learning invariant to image degradation, occlusion, and image complexities. Here we have shown some examples. Top right is the original image. Top left is the original image. Top right after performing some random masking. Bottom left after applying 30% Gaussian blur. And bottom right after applying both random masking and Gaussian blur. And we also conducted some exhaustive experimentation. The proposed detection framework has been trained on 4 publicly available benchmark datasets. These include ICDA 2015, ICDA 2017, MSR-ATD 500, and COCOTEXT. We trained our Gabor convolutional layers with 4 orientation channels and set the scale at 4. The proposed architecture is trained using momentum optimizer with an initial learning rate of 0.01 and momentum 0.9. We used random mirroring, resizing, and variations in brightness and contrast for each sample towards data augmentation. Now let us describe some comparative results. Results of our model in comparison with other SOTA models on ICDA 2015 dataset is shown in this slide. From this slide, we can see that on this dataset, our model performs better than all other SOTA models corresponding to each of the detection and end-to-end recognition tasks. In case of detection, with respect to each of the 3 measures, recall, precision, F-score, our model outperforms all the other SOTA models. And the similar thing happened for the end-to-end recognition task. When we consider ICDA 2017 dataset, we have observed similar thing. Here also with respect to detection, corresponding to recall, precision, and F-score measures, our model has outperformed all other SOTA models. But when we consider MSR-ATD 500 dataset, our model has outperformed existing SOTA models with respect to the measures precision and F-score only, but it is only the second best with respect to the measure recall. And when we consider COCOTEXT dataset, our model performed best for the end-to-end recognition task, but for the detection task, our model could not outperform the SOTA model with respect to the precision measure. But with respect to other 2 measures, our model outperformed the SOTA models. And here we have shown some visual results, and the results, if we see, we can see that the results are quite encouraging. Finally, let us conclude our work. Here, we introduced a novel multitask learning framework for syntax spotting. The domain classifier module takes care of the domain adaptation task, which helps to compensate the shift in distributions between training and test data sets of samples. Here we have introduced a novel regularizer component into the multitask loss function to control the learning of individual strata of the FRB. Also, we used a mask and predict strategy to enable the network to take care of partially uploaded text. We conducted extensive simulations on 4 benchmark datasets like ICDA 2015, ICDA 2017, COCOTEXT, and MSR-ATD 500. And proposed framework efficiently detects incidental syntax independent of its language. Thank you.